Hello, thanks for listening. This is my individual reading homework about the sampling-based algorithm. My name is Yihao Cai, and the thesis I've chosen for this reading is virtual goal guided RRT for visual serving the mobile robots with field of view constraint, which also corresponds to my project. And for the sampling-based method, here is the pipeline of it. First, we received the roadmap with the uh, available configuration as well as the uh, collision part on it, and then we implement sampling methods with something like PRM algorithm, RRT algorithm, and then we get a renewed map. After that, we just use the map construction method, like the KD train or some extension ways to make it more complete. And after that, we can also use the map optimization method like rewiring or uh, revalue for the cost of each node. And in this way, we get an optimized map. And for here, we have built an entire construction step. And if we want to get a plane trajectory for with the starting and goal point, we have to take the query step using some method like a star and dijkstra and something like that. And this is the profile for the sampling based method. As for the proposed approach in the thesis, first, it is about the visual serving. So, I just want you guys to know about its application in the world. Like, it is as wide a range of application area in the either the service robot or the industry robot. And here is the something about the visual serving. As for the thesis, we first came up, as usual, we first came up with the research questions. For the first, what is the camera problem using visual serving methods? And the answer is that it exists non-holonomic constraint, a field of view constraint, and the unknown image depth, and something like that. And for the second questions, uh, since we got the visual feedback from the visual serving method, how to fully use the real-time visual feedback? And the answer is we keep the feature points. We think up ways to keep the feature points in the camera field of view during the whole visual serving process. And the final questions came to us that how to address these two problems above. And in their paper, the author has came up with the VGGRRT algorithm, which is based on the camera field of view, and I will talk about it later in a very detailed way. And okay, here comes the problem description. These are the situation the author has think up a bit of ways to solve the real practical problems in reality, and here he just used this shape as their mobile robot, and because it is a 2D plane, so its pose is defined with three vectors which noted are x, y, and also the theta as its orientation. And the main tasks for this problem is to think up of all the ways to drive the mobile robot from the current pose to the desired pose. And as you can see that there is a camera attached on it to capture the frames from the neighborhood. And also it demands that we have to keep the feature point, which is also the interesting object we want to observe using this camera, to make the feature points within the camera field of view all the time when it gets along the way to the desired pose. And that is the specific requirements for this certain tasks. And thereby, by math calculation, we get the discrete pseudodynamic model, which noted as follows. And here, k plus 1 means it is the next state of time that x star will get to with time goes by. And there are also some parameters that we can think out that we can figure out its physical meanings, like the xy are the scale coordinates value for the mobile robot, and v omega, also known as the linear angular velocity, the theta as the orientation angular, and a1 and a2 is the linear algorithm acceleration. Delta t is also known as the integration step, which you can also regard as the interval time. And with some basic physics and math knowledge, you can easily get all the formulas. And there is something to be noted that x star represents the scaled coordinate, because we lost the depth from the visual survey, because we get the object from a 2D image, so we can hardly estimate its depth. So x is the exact point the mobile robot is, and the x star is the estimation ones according to the distance from the desired frame arranged to the feature point plane. And this is the approach framework for the proposed method in this thesis. Firstly, the author gets the initial image of the feature point, and also it proposed the desired image within it, and therefore they just want to get an estimated pose from the scaled space, and thereby they just think up their algorithm to generate the trajectory and make the trajectory planning in their 3D scaled trajectory space. After that, they get the projection to the image trajectories, which means that they will compute pixel coordinates in the meanwhile, and also they will help check their camera field of view to make sure the camera stays in the field of the feature point stays in the camera view for all the time in the whole process. And for this whole part, we call it trajectory planning phase. And for the next, after it has get the plane trajectory for the mobile robot, it starts to execute it. So this phase is also known as trajectory tracking control phase. For this phase, the mobile robot receives the planned trajectory and executed them one by one. In the meanwhile, it has the virtual tracking controller to uh, to control the robots uh, along the way with the parameters set uh, and and all its controller variants are set to be the negative feedback for this whole part to make the mobile robot state in reach the goal in a more accurate way. And after that, we can talk about the VGGRRT algorithm, and it is also the core part of this whole thesis. Okay, for this algorithm, it is very similar to RRT. It is also has the general searching phase, which is also defined in RRT algorithm. Like it will first initialize the tree and generate a virtual goal, which is very similar to RRT, and after that it will execute the it will get the random node either by the generated virtual goal or the generated random state according to the probability. And also this figure has illustrated the whole part in a precise way. This is the virtual goal that has been generated in the during this process, and it has been generated in the way that it has the same longitude with the initial pose, and it has the same latitude with the desired pose. So there are two arrows showing this. Also, the benefit that we generate the virtual goal is, for the first, to make generated candidate edges easier to satisfy the camera field of view constraint. And for a second, we reduce the mobile robot lateral error, which I will talk about a lot later. And in this way, other processes are somehow the same as the process in RRT algorithm. It will also detect its nearest side nodes from its neighborhoods, which is shown vividly in this picture. And all this part is called general searching part, which is somehow like RRT. And this part is called the grid extension, and this is also the second part that the VGGRRT algorithm differs from the purely RRT algorithm. And for this grid extension process, it has the polar stabilization controller, which is defined in this formula, and there are also the explanations for the parameters here. All that it wants is to generate extend the point to reach the final goal. And here from the pseudocode you can see the purpose of this algorithm and this step. And that is all about the algorithm. Here comes the camera field of view constraint checking, and also here is the very important process in the whole pipeline. As we all know, that the current image and the desired image are two images, and they they both can be transferred to each other by projection, and the specific method is called homography matrix decomposition. Okay, here are the specific math calculation about how one how one how to from one image to get the projection to another. And for the first, we can define the feature point plane as a vector n, and then we calculate the Euclidean homography matrix H, which is denoted as the following, and the parameters are also explained by this. If you have learned something about the robot dynamics or robot foundation, you can understand these you can understand this so very quickly. And after all this has been achieved, we get the projective homography matrix G, and by K plus H plus inverse of K. Here, K is the intrinsic parameter matrix of camera, which can be found easily with their camera parameters predefined. And after that, we can get the pixel projection by this formula. And here, PID means the pixels that is on the desired image, and PI means the pixel means the point that is on the current image. And thereby, in order to make the feature point in the field of view of camera, we have to limit its conditions as PIY and PIZ, which is also the pixel coordinates of the point in correct image. And in this way, we can guarantee that the point is in the range in the field of view of camera, and all these conditions composed of a very complex formula, and we can calculate all of them by only implementing these constraints. And this whole process is called camera field of view constraint checking. Now here is the experimental result for this paper. They have actually conducted the experiments for two purposes. The first is that they tested the effectiveness of their approach. Here, they have just attached the pictures, tested their scenarios, compared with the small initial lateral error and the large initial lateral error. For the lateral error, it is a word or it is a noun that measures how close the point in a picture is to the boundary of the images. For example, if a point is here, it is very close to the image boundary. But if the point is here, it is slightly far. It's slightly far away from the image boundaries. And in this situation, they have tested this more initial lateral error. Under which situation there is slightly difference between the traditional method and the method they have proposed. However, for the large initial lateral error situation, uh, they have get the result that the one which is implemented with the method they proposed has a much better performance than the one with the traditional method. And in this way, they proved the effectiveness of this proposed approach. And for the experiment 2, they tested the necessity of the approach. And here, have also conducted a virtual experiment to explain this, by which you can observe the result obviously from the pictures attached to this slide, and this is the one that they use the proposed approach, and this is the one that they use the virtual stabilization controller. And in this situation, the mobile robot follows the trajectory like this. It goes to this, and from here, and during the auto process, this picture has shown the image feature trajectories of the robot, which from which you can observe that all these trajectories are within their boundary of their whole images. However, if they use the visual stabilization controller, the mobile robot goes from the origin to the design point in this way, and they get the image feature trajectories that the initial image goes from here, and from which you can observe that it has exceeded the boundaries of the whole pictures. And also, this denotes the necessities of this approach if you want to make sure that the feature point is within the camera field of view constraint when applying the mobile robot during the whole process. And here is the paper summary. For first, this proposed approach includes two-level framework for robot visual surfing. And as I explained, one is the trajectory planning, and another is the visual tracking using a visual tracking based controller. And the second is that they have just designed a VGG RRT planning algorithm for the first phase, and this algorithm differs from traditional RRT in that it sets a virtual goal and it has a polar stabilization controller, which also benefits these by achieving better aim accuracy. For the third, they have tested the probabilistic completeness analysis and to validate the feasibility of the algorithm for practical implementation. And for the last one, they have just set up the two experiments to show the effectiveness as well as the necessity of the proposed framework. And that's the summary for my presentation, and thanks for your listening, and thanks for your time.